Okay, so I already wrote the third case, positive, negative eigenvalue. Again, here's the example. Take a moment to write it down, and that's the solution. And notice we have lambda equals 1 positive eigenvalue, and the second one -2 negative eigenvalue. So this is what we're going to call a saddle. And it's another example of an unstable solution or an unstable equilibrium point. Though it's unstable, I mean, the way we define it, that stability means that if you start on a neighborhood of the point, the solutions approach that point. And you will see that that's actually not true for any point except the one starting on the eigenvalue corresponding to -2. I just, for simplicity, I put this in the category of unstable because this notion of stability, or whether it's unstable or stable, can be broken down in sub-cases. Again, if you want to have a more refined description. Even the notion of stability, actually, it's split into what's called asymptotic stability or just stability. I don't want to go into that level of details. Suffices to say that this is different than an attracting node in the sense that, or different than a repelling node in the sense that the solution will move away from the equilibrium unless you really start on the eigenvector corresponding to -2. Because think about this, if you have both of these non-zero, so if you have both these constants non-zero here, this portion here will move the solution towards 0 for a while, but eventually this one takes over because this goes to infinity while this one goes to 0 eventually. So the effect of the negative eigenvalue vanishes as t goes on, as t goes to infinity, because this whole part approaches 0. And that's what actually creates the saddle shape, as you'll see. So each of them, again, each eigenvector is invariant like before. So when you sketch what happens here, just like before, you can start with the eigenvectors themselves. So the one corresponding to the -2 is 1, 1, like here. And the other one corresponding to 1 is 1, 4. I should have, let's see, if you can squeeze it in here. So that's going to be 4. 1, 2, 3, 4, roughly speaking. Actually, better examples are for a saddle are when you have these eigenvectors more away from each other, but it's still fine. So anyway, this one here corresponding to -2, if you start on it, the solution approaches 0 right on that vector, and on the other one, it moves away from 0. So the only way you approach 0 is if you start on this eigenvector corresponding to lambda equals -2. For all other solutions, the effect of both eigenvectors will happen, right? So if you start here, this guy pulls the solution towards 0 for a while, but then it moves away from 0 because of the other guy, the other eigenvector. Same thing here, towards 0 for a while because of this, and then away from 0. In between them, same idea. It's gonna look kind of squeezed here, but it's like that basically, right? So towards 0 because of this, away from 0. Same thing here, right? So then you have the so-called saddle shape around the equilibrium point. Again, as I mentioned before, stay tuned and run these examples with a computer because the picture will be much, much better, obviously. By the way, for the purpose of testing it on paper, I may ask you to sketch an eigenvector, the eigenvectors, these straight lines, and maybe 1 or 2 lines like this, just to indicate that you actually have an idea how the solution looks like, roughly speaking. So I'm not gonna expect a pretty picture or a detailed one, but enough to actually show that you understand what the shape is all about for each case. So the next one I want to go over now, let's do the star node just for simplicity. I mean, just for completion, what I mean, because not for simplicity, just for the completion of the whole classification. I told you before that in a 2x2 case, the star node is not important because it corresponds to decoupled systems that can be solved equation by equation. So you don't have to go through the whole system theory to deal with it, but because the geometry is so different, we should mention this case separately. So this is the case when you have a single eigenvalue and 2 eigenvectors. Again, a correct way of saying it is that the eigenspace is the entire the entire plane, because the eigenspace has dimension 2. So any vector is an eigenvector. So if you don't remember what I'm talking about, go back to the previous lecture and take a look at the part when I actually dealt with a system like this. So for example, the matrix, let's say it's 2, 0, 0, 2. This is the case when you have a single eigenvalue, but 2 eigenvectors. Like the eigenspace is given by 2 independent vectors. 1, 0, e to the 2t, plus c2, 0, 1, e to the 2t. So notice you have the same lambda, but you have 2 different eigenvectors which form a basis, and they generate essentially the entire plane. I mean, remember from linear algebra, 1, 0, 0, 1 generates via linear combinations the entire plane. So any vector, any vector is an eigenvector, which means any vector is a straight line solution. Remember what I told you before, eigenvectors correspond to straight line solutions, which is the reason why you have this star node, in this case unstable, because lambda is greater than 0. So when you look at the picture here, all you see when you click on various solutions, you'll see straight lines moving away from 0. So the opposite case of this, or the opposite one in terms of the stability, single eigenvalue, 2 eigenvectors, but with lambda negative. So let's say x prime is equal to minus 2, 0, 0, minus 2, x. And of course, the solution in this case will be a combination of 1, 0, e to the minus 2t plus 0, 1, e to the minus 2t. So the mirror image of this, but now with the arrows moving in toward the origin. Okay, so you have what is called a star node, stable or attracting. So remember, the goal is to establish the stability and some geometric description of the solutions around the equilibrium point. So that's why it's worth noting it as separated cases, because of the straight line solution for any point you pick on the phase plane. Let's move on now with what we call later the case of a degenerate node. That is when you have a single eigenvalue like here, but a single eigenvector. So let's say case 6, right? This is the so-called degenerate node, right? So I mean, degenerate node, which means single eigenvalue, single eigenvector. So let's take the positive case first. Say lambda 1 equals lambda 2 equals, let's see which one, 1. And the example that I picked is given by the matrix minus 1, 2, minus 2, and 3. I didn't actually bother to write the solution here. So let me just mention the eigenvector. So the only eigenvector here for 1 is going to be 1, 1. Yeah, because that's what I need actually to, look at the picture of what you get here. So it's called the degenerate case because it's like the two eigenvectors, which appear like that, right? Collapse into 1, right? So like doesn't look good. I don't have any way to explain, but the thing is, if you imagine the two eigenvectors, the two straight line, imagine that the two straight line collapse into 1. because that's why also it's called, when I say single eigenvalue, it's like a double root, right? I mean, when you find this root, it comes from lambda minus 1 squared. So imagine the two eigenvectors collapse into one, so you have just one straight line solution. Pretty much like the nodes you saw before, attracting node, repelling node, but only with one straight line solution. So the picture looks kind of like this. So let's put it here. So the vector, the eigenvector is 1, 1. And then otherwise, and then of course, because lambda is positive, the solution moves away from 0. And then wherever you start, any other initial point, the solution moves away from 0 like that. So it's like a repelling node in which the two straight line solutions collapse into a single one. Sometimes, depending on the value of lambda, sometimes this is confused with a spiral point in the complex case, as you'll see. But the dead giveaway that you have a single eigenvalue, single eigenvector, or the degenerate node, is when you have a straight line solution. You clearly see that all of them are spiraling, I mean, like moving away like that or towards 0, but there is only one straight line solution. So because it moves away from 0, this is the case when lambda is positive. So this will be, of course, a repelling degenerate node. Right? It's the analogous of a repelling node when you have two different eigenvalues, both positive. So this is the same case, but with a single eigenvalue, single eigenvector. And let's finish this part with the opposite case when you have the same configuration but with negative lambda, right? So lambda 1 equals lambda 2 equals lambda less than 0. This will be a repelling, excuse me, an attracting degenerate node. And the example that I picked is x prime equals 1 and 2 minus 2 minus 3. So the same trick, you just change the signs of the main diagonal and you get the same eigenvalue but with the opposite sign. So this will give you lambda equals minus 1, which is clearly negative. And the eigenvector, if you take the time to compute it, will be 1 minus 1. All right, so the picture looks like this. Eigenvector 1 minus 1. On it, if you start on it, you move towards 0. And all other solutions will move towards 0 as well. Like that. I'm not really good at this, obviously, with the picture. But roughly that's the idea, okay? So the opposite of this. Now of course, the eigenvector is different. That's why the line you see here, it's different than this one, right? But same idea, right? I mean, the solution moves now towards 0. All other solutions curve towards 0 as well. Only one straight line solution corresponding to the only eigenvector. So this basically is the classification when you have non-zero eigenvalues. Zero eigenvalues are a special case. I usually don't insist too much on it, but again, let's make this classification complete because it's interesting as a point of discussion and also to see how the geometry looks completely different. And also even the notion what's an equilibrium point is going to be different if you have zero eigenvalues. So stay tuned for the next part.